Hello everyone, this is 6.4 Speed of Sound and Echoes. Introduction. Firstly, these days in winter, all of us we experience the thunder or the lightning. Okay, sound is much slower than light. Sound is much slower than light. How we experience this one, or how do we know sound is slower than light? When it will light here, what is happening? Firstly, so you will hear lightning after you see it. So firstly, you will see the light after a while, after a couple of seconds. For example, you will hear the sound. In fact, the sound and the light, they are happening at the same time, but we see the light firstly, and then we hear the sound. Why this is happening? Because the sound waves are much slower than light. The speed of sound. The speed of sound, it's known. The speed of sound in air, okay, in air the speed of sound is about 330 meter per second. Okay, that is slower than Concorde. Concorde, it's a plane, okay, but about 4 times faster than a racing car. So again, speed of sound in air, okay, it's 330 meters per second. Then here we have some facts about speed of sound. The speed of sound, it depends on the temperature of air. So what's that mean? As much as sound waves travel faster through hot air than cold air. So when the temperature increase, the speed of sound also it will increase. Okay. Again, when the temperature increase, the speed of sound also it will increase. Then number 2, the speed of sound does not depend on the pressure of the air. If atmospheric pressure changes, the speed of waves stay the same. Okay, so speed and atmospheric pressure, it will not affect. It's the same thing. Then the speed of sound is different through different materials. What do you mean by here different materials? We have solid, liquid, gas. The speed of sound, okay, it differ in these 3 materials. For example, here we say the speed of sound in air, it's 330 meters. Okay, here we say it in air, but this speed in solid, in liquid, it will change. It will not be the same. So sound waves travel faster through liquid than gases, and fastest of all through solid. There are some examples. We will talk about some examples later. Okay, again, sound, the speed of sound is different through different material. So sound waves travel faster through liquids than gases. So now if you will have a question, it says the sound waves, it's faster in gas or liquid. So what you will say? You will say in liquid. Okay, sound waves travel faster through liquids than through gases, and fastest of all through solid. Okay. Measuring the speed sound, or how do we know here when in this slide when we say the speed of sound it's 330 meters per second in air. How do we know it's 330? Okay, so as you can see here, it's the device that they use to measure the speed of sound. This device, it consists of microphones, two microphones A and B, okay, and control unit, and with a digital timer. It's like a stopwatch, okay. And here we have a source of sound. Okay, so the speed of sound in air can be measured as shown below. Okay, a sound is made by hitting a metal block. So here we have this metal block. They will hit it, so it makes sound. This sound, it goes until it will reach microphone A. Microphone A, as you can see, it's connected with the control unit. Start. What do you mean by start? The timer will start. Then, when the waves it reach B, again another signal, it will stop the digital timer. So again, block, they will hit the block. This block will make sound. This sound here in the microphone A, when the sound it reach, or when the waves it reaches microphone A will give a order to the control unit to start the timer. Then when the waves it reach the microphone B, again the microphone will give order, or will give a signal to the timer to stop. Now here, from microphone A to microphone B, there is a distance, a known distance. This distance, okay, it's about 1 meter, okay. So here we have about 1 meter. Okay. If B is 1 meter further away from the A, okay. And now what do we have? We have distance, and we have the time, which is 3. So by applying this equation or this formula to measure the speed of sound equal to distance traveled over time. So how much was the distance traveled? It's 1 meter, because we say the distance between microphone A and microphone B, it's 1 meter. Then the time, how much time it took? So it took, as you can see here, it's written 0.003 seconds, or 3 milliseconds. So 1 meter over 0.003 second equal to 330 meter per second. So this is the way by which we got the speed of sound. Here, if you look at this table, it shows speed of sound through air, dry air, at 0 Celsius, it's 330. Air dry at 30 Celsius, it's 350. So this, it proves that the speed of sound depends on the temperature. We said as much as the temperature increase, the speed also it will increase. So here what is happening? Here we have the temperature. Here it was 0, then here it's 30. What happened to the temperature? It increased. Again, also what happened to the speed? It increased. It was 330, now it's 350. And here in water, okay, in water, pure water at 0 Celsius, it's 1400 meters per second. In concrete, which is solid, it's 5000 meters per second. Okay, so again here this table, it shows that what we said here, sound travel faster through liquid than gas and fastest in solid. So firstly, solid, it's number 1, liquid number 2, and gas it's number 3. Okay, now if you look here, in which of these materials is fastest? It's in concrete. Concrete, it's solid, so this is number 2. Water, it's 1400, it's number 2. And also here air, both of them are gas, so here it's number 3. Refractions of sound. Again, before I start explaining this one, you should know what do you mean by the word refraction. The word refraction, or the term refraction, it means bending the wave. Okay, so here we have example which is about train. This train, it says during night the sound of it's louder. The sound of trains at night, it's louder than sound of trains during the rest of day. Okay, now what's the difference between day and night? What's the main difference between them? Okay, or what is the thing that it will change in day and night? Okay, the answer is what? It's the temperature. The temperature during day and night, it will change. Of course, when it will be more and when it will be less. During night, it's less. So, distant trains and traffic often sound louder and closer at night. Okay. The reason in this is this: during the night time when the ground cools quickly. Okay, so here what happened? The temperature, it changed. At night, the roads or the ground, it will cool faster. Okay, air layer near the ground become colder than those above. Okay, so here it's the ground. So here we have cold air and here it's warm air. So what will happen here? Sound waves travel more slowly through this colder air. As a result, waves leaving the ground tend to bend back toward it. So if we want to draw it, we will draw it in this way. Here it's the sound waves. It's coming in this direction. Okay? When it will try to raise or to go higher, a cold air will bring it down again. Okay, so as you can see here, what happened? The sound, it's bending. Okay, because the sound it's bending, okay, instead of spreading upwards, a bending effect, the sound will bend. A bending effect like this caused by a change in speed is called refraction. Okay, again, here the sound, here it's cold air, and instead of going higher or going up, the sound waves, it will bend. What do you mean by bend? Here this bending, it's what? This is the refraction. Why it's bending? Because the speed of these waves is changing. Why the speed of these waves it's changing? It's changing because of the change in the temperature. Echoes. Echoes, what do you mean by echoes? As we explained before, echoes, it means it's bouncing the sound. Okay, it's as I mentioned in the last lesson, we said sometimes when you will talk, you will hear your sound back after a while. Okay, this we called it echoes. Okay, but why? What happened? Why you are hearing your sound again? We will explain it now. If you look at this drawing, it shows, okay, this person, he made sound. This sound, it's traveling by this direction. Okay, what do we have here? We have a hard surface. Hard surface. This hard surface will what? Will reflect the sound. So, reflecting the sound, this is what they mean by echo. Okay, so hard surfaces such as walls reflect sound waves. When you hear an echo, you are hearing a reflected sound short time after the original sound. In the diagram on the right, it's like as I just explained, okay? So if you want now to calculate or to find the time, how long it took the echo to happen, okay? So again, speed of sound, distance traveled over time. But one more thing about echo, always, okay, you should focus or connect between echo with this number, with number 2. Why 2? Okay, here, if, now let's say, for example, if the distance between this person, okay, and this one, let's say it's 5 meters, okay, but the distance between this person and the wall, it's 5 meters. Now, what is the total distance that the sound it took or traveled? Now, from this person to the wall, it's, for example, let's say it's 5 meters. Okay? And from the wall to this person, also it's 5 meters. Now, how much is the total distance that the sound it traveled? Now, it's 5 plus 5 equal to 10. So, if we want to find speed or the distance or the time or sound, any one of this, if the question is about echo, we should focus on this number, which is 2. So now, the formula, it will be speed of sound equal to 2 times distance to wall and over time. Okay? Then, here we have some uses. The principle of echo is used in several devices. For example, echo sounder. What do you mean by echo sounder? It's a device that they use to measure the depth of water under a boat. If you, here is the example. Here we have the boat or the ship. Okay. Here, firstly, it sent waves. These waves, it goes to this direction. Okay. Then it will be reflected. When it will be reflected, here we will have a receptor or a device that it will receive the waves. Now, what do we have here? We have the speed, it's known. We know how much, here we know how much is the speed. Okay, and we are calculating the time, how long it took the wave to travel from the boat, goes and comes. So now we have speed, we have time. What we can find if we have speed and time, we can find the distance. Okay, so in this way we will know how deep is this sea or how deep is this river or any kind of water. Another example of using of echo, it's parking sensors. Parking sensors, what do you mean by parking sensors? As you know, most of the new brand cars now, they have sensors, okay? These sensors at the back and sometimes also it found in front of the car, But let's talk about the one that is at the back of the car. Okay, when a car is moving back or trying to park the car, okay, when these sensors, it sent waves to the any surface. Okay, so when this waves, it hit the surface and it bounce. When it bounce, okay, so here what will happen, well, that it will calculate the time, okay, how much time it took to send and receive, and also the speed of it, it's already known. So if we again, if we have if we know the speed and we know time, so we can find the distance. Radars also, the same principle. It depends on sending waves. So a radar will send a wave, it will hit a ship or a plane, okay, and then will bounce. So radar, the waves, it's going to the object, hit the object, it bounce from the object, then will be received again by the radar. So here what will happen, again we are having the we know the speed of the wave and also how much time it took, so then we can detect or we can calculate the distance between the radar and the object. Okay, now math questions. Assume that the speed of sound in air is 330 meters per second. So this part will be included for all the coming questions. Okay. Number one, why do you hear lightning after you see it? Again, as we explained here, why you see the light, then here you hear the sound. Why do you hear lightning after you see it? Again, the reason behind this is the sound waves are slower than light waves, okay? Or you can say the opposite. The light, it's faster than sound. Okay, math question. If a lightning strikes and you hear it 4 seconds after you see it, how far is it? In math questions, as we said before, the first step to solve the questions, to solve the math questions, it's by what? It's by writing the information. Firstly, what are the informations that we have? Okay, they said a lightning strikes and you hear it 4 seconds. So what's this? Time. So time equal to 4 seconds. After you see it, how far away is it? So they are asking to find what? The distance. So how much is the distance? We don't know. Now, as we said, you will depend on this one, okay? Sound in air. So what do we have here? We have speed. Speed equal to 330 meter per second. Now, how to solve it? We will write the formula. Speed equal to distance over time. Now, how much is the speed? 330 equal to. How much is the distance? We don't know. We want to find it. So, and over time, how much was the time? It was 4. Okay, so now distance equal to 330 times 4. Distance equal to, okay, so the answer will be 1320. 1320. Last thing, don't forget to write what at the end? The unit. So we found the distance. So which unit do we use for measuring the distance? We use meter. Okay, the rest of questions, it's your homework. Okay, does sound travel faster through cold air or warm air? Okay, I will solve the first one for you. The second one will be you will solve it. So here what do we have? Cold air, warm air. So here we are talking about what? We are talking about different in temperature. As we explained in the second slide, okay, we said as much as the temperature increase, the speed it will increase. So of course the answer will be what? In warm air. Warm air, it's the correct answer. B, a solid or gas. This is your question. Okay, the rest of questions, it's yours. Solve it. Thank you so much. Again, any questions, don't hesitate to text me. Have a good day.